Welcome to an enlightening journey into the world of artificial intelligence, AI. This presentation is designed to provide you with a solid foundation in AI, covering everything from its basic concepts to advanced applications. Whether you're a curious beginner or an aspiring AI professional, this guide will equip you with the knowledge and tools to understand and navigate the exciting field of AI. We'll explore the evolution of AI, delve into its various types, and examine its profound impact on modern society. You'll learn about the essential mathematical concepts, programming foundations, and core principles of machine learning and deep learning. By the end of this presentation, you'll have a comprehensive understanding of AI and be well prepared to take your next steps in this transformative field. Definition: Artificial intelligence refers to the simulation of human intelligence in machines programmed to think and learn like humans. It encompasses a wide range of technologies and approaches aimed at creating intelligent systems. Key aspects: AI involves machine learning, natural language processing, computer vision, and robotics. These components work together to enable machines to perceive, learn, reason, and interact with their environment. Goals: The primary goals of AI include problem-solving, decision-making, and task automation. AI systems aim to augment human capabilities and improve efficiency across various domains. 1950s to 1960s, birth of AI. The term artificial intelligence was coined in 1956 at the Dartmouth Conference. Early AI focused on problem-solving and symbolic methods. 1970s to 1980s, AI winter. Enthusiasm waned due to limitations in computing power and algorithmic approaches. Funding and interest decreased significantly. 1990s to 2000s, revival. Advances in machine learning and increased computational power led to renewed interest. AI began to solve real-world problems. 2010s present, AI boom. Deep learning breakthroughs, big data, and cloud computing have propelled AI into mainstream applications across industries. Artificial superintelligence, ACI. Hypothetical AI surpassing human intelligence in all aspects. Artificial general intelligence, AGI. Human-level intelligence across various domains. Artificial narrow intelligence, ANI. Specialized AI for specific tasks, currently prevalent. Artificial narrow intelligence, ANI, is the most common form of AI today, excelling in specific tasks like image recognition or language translation. Artificial general intelligence, AGI, aims to match human-level intelligence across multiple domains, while artificial superintelligence, ACI, represents a theoretical future where AI surpasses human capabilities in all areas. Healthcare. AI assists in diagnosis, drug discovery, and personalized treatment plans, revolutionizing patient care and medical research. Finance. AI powers algorithmic trading, fraud detection, and personalized banking experiences, enhancing efficiency and security. Transportation. Self-driving cars and optimized logistics are transforming how we move people and goods, increasing safety and efficiency. Education. AI enables personalized learning experiences, intelligent tutoring systems, and automated grading, revolutionizing education delivery. Vectors and matrices. Vectors represent data points or features, while matrices store and manipulate large datasets. Understanding operations, like dot products and matrix multiplication, is crucial for AI algorithms. Eigenvalues and eigenvectors. These concepts are fundamental in dimensionality reduction techniques like principal component analysis, PCA. They help in understanding the underlying structure of data and optimizing computational efficiency. Linear transformations. Linear transformations form the basis of many AI algorithms, especially in neural networks. They allow for the manipulation and analysis of high-dimensional data spaces. Probability distributions. Understanding various distributions like normal, binomial, and Poisson is essential for modeling uncertainties in AI systems. Bayes' theorem. This fundamental concept forms the basis of many machine learning algorithms, especially in classification and decision-making tasks. Statistical inference. Techniques like hypothesis testing and confidence intervals are crucial for evaluating model performance and making predictions. Sampling methods. Understanding various sampling techniques is vital for working with large datasets and ensuring representative data for training AI models. Derivatives and gradients. Essential for understanding how neural networks learn and optimize their parameters during training. Chain rule. Crucial for implementing backpropagation, the key algorithm for training deep neural networks. Partial derivatives. Necessary for working with multivariable functions in complex neural network architectures. Optimization techniques. Methods like gradient descent rely on calculus to find the optimal parameters for AI models. Objective functions. These functions define what the AI model aims to maximize or minimize, such as minimizing prediction errors or maximizing reward in reinforcement learning. Constraints. Optimization problems often have constraints that limit the possible solutions, reflecting real-world limitations or desired properties of the model. Optimization algorithms. Various algorithms like gradient descent, Newton's method, and evolutionary algorithms are used to find optimal solutions efficiently. Convex optimization. A special class of optimization problems with guaranteed global optima, often encountered in machine learning and AI applications. Python. Widely regarded as the go-to language for AI and machine learning due to its simplicity, extensive libraries, and strong community support. R. Popular for statistical computing and data analysis, with powerful packages for machine learning and visualization. Java. Offers robust performance and scalability, suitable for large-scale AI applications and enterprise environments. Julia. A rising star in scientific computing and AI, known for its high performance and ease of use in mathematical computations. Python's ecosystem offers a rich set of libraries for AI development. NumPy provides efficient numerical computing capabilities, while Pandas excels in data manipulation and analysis. Scikit-learn offers a comprehensive set of machine learning algorithms. For deep learning, TensorFlow and PyTorch are the leading frameworks, each with its strengths in building and deploying neural networks. These libraries work seamlessly together, allowing developers to quickly prototype and scale AI solutions. Their extensive documentation and community support make them invaluable tools for both beginners and experienced AI practitioners. Arrays and matrices. Fundamental for representing and manipulating data in AI applications. Efficient array operations are crucial for performance in large-scale AI systems. Trees and graphs. Essential for representing hierarchical data and complex relationships. Decision trees and graph neural networks are examples of AI algorithms leveraging these structures. Hash tables. Provide fast lookups and are used in various AI algorithms, including feature engineering and caching in neural networks. GIT basics. Learn fundamental GIT commands for version control, including commit, push, pull, and branching. GitHub or GIT Lab. Utilize online platforms for code hosting, collaboration, and project management in AI development. Code reviews. Implement peer review processes to ensure code quality and knowledge sharing within AI teams. CI/CD for AI. Set up continuous integration and deployment pipelines tailored for AI model development and deployment. Definition of machine learning. A subset of AI that focuses on algorithms that improve automatically through experience and data usage. Types of machine learning. Supervised, unsupervised, and reinforcement learning, each with distinct approaches to learning from data. The learning process. Understanding how machines learn from data, including feature extraction, model training, and evaluation. Applications of machine learning. Exploring real-world applications across various industries, from recommendation systems to autonomous vehicles. Supervised learning. In supervised learning, the algorithm is trained on a labeled dataset, where each input is paired with the correct output. The goal is to learn a function that can predict the output for new, unseen inputs. Common applications include image classification and spam detection. Unsupervised learning. Unsupervised learning deals with unlabeled data, trying to find patterns or structures within the data without predefined outputs. This approach is used for clustering, dimensionality reduction, and anomaly detection tasks. Classification. Predicts categorical class labels. Examples include logistic regression, decision trees, and support vector machines. Regression. Predicts continuous numerical values. Techniques include linear regression, polynomial regression, and neural network regression. Ensemble methods. Combine multiple models for improved performance, such as random forests and gradient boosting machines. Deep learning. Neural networks capable of both classification and regression tasks, especially effective for complex, high-dimensional data. Data splitting. Divide data into training, validation, and test sets to ensure unbiased evaluation of model performance. Training process. Iteratively adjust model parameters to minimize error on the training data. Validation. Use validation set to tune hyperparameters and prevent overfitting. Final evaluation. Assess model performance on the unseen test set using appropriate metrics. Overfitting. Occurs when a model learns the training data too well, including noise and outliers. This results in poor generalization to new, unseen data. Overfitting is characterized by high accuracy on training data, but low accuracy on validation or test data. Underfitting. Happens when a model is too simple to capture the underlying patterns in the data. Underfitting models perform poorly on both training and test data, indicating that the model hasn't learned the relevant features of the dataset. K-fold cross-validation. Divide data into K subsets, train on K1 subsets and validate on the remaining 1, rotating K times. Stratified K-fold. Similar to K-fold but ensures each fold has the same proportion of samples for each class as the complete set. Leave one out cross-validation. Use all but one sample for training and validate on the left-out sample, repeating for each sample. Time series cross-validation. Specialized technique for time-dependent data, using past observations to predict future ones. Input layer. Receives raw data features. Hidden layers. Process and transform data. Output layer. Produces final predictions. Neural networks are inspired by the human brain structure and function. The input layer receives the initial data, which is then processed through one or more hidden layers. Each layer consists of neurons, nodes, connected by weights. The output layer produces the final prediction, or classification. The network learns by adjusting these weights based on the error between predicted and actual outputs, using techniques like backpropagation and gradient descent. Sigmoid. Used in binary classification problems. Squashes input to range 0, 1. ReLU. Rectified linear unit. Popular in hidden layers for its simplicity and effectiveness in reducing vanishing gradient problem. Tan. Similar to sigmoid, but outputs range from -1, 1. Often used in recurrent neural networks. Softmax. Used in multiclass classification problems. Outputs probabilities that sum to 1. Forward pass. Input data propagates through the network, generating predictions. Error calculation. Compare predictions with actual values to compute the loss. Backward pass. Propagate the error backwards, calculating gradients for each weight. Weight update. Adjust weights using gradients to minimize the loss function. Convolutional layers. Apply filters to input data to extract features. Effective for processing grid-like data such as images. Pooling layers. Reduce spatial dimensions of the data, making the network more computationally efficient. Fully connected layers. Combine features extracted by convolutional layers for final classification or regression. Applications. Widely used in image and video processing, including facial recognition and object detection. Sequential data. RNNs are designed to work with sequential data like time series or natural language. Memory cells. Contain loops allowing information to persist, creating a form of memory. LSTM and GRU. Advanced RNN architectures that address the vanishing gradient problem in long sequences. Applications. Used in speech recognition, language translation, and time series prediction. Concept. Transfer learning involves using knowledge gained from solving one problem and applying it to a different, but related problem. This approach is particularly useful when you have limited data for your target task, but abundant data for a similar task. Benefits. Transfer learning can significantly reduce training time, improve model performance, and enable effective learning with smaller datasets. It's widely used in computer vision and natural language processing tasks. Techniques. Common techniques include fine-tuning pre-trained models, feature extraction, and domain adaptation. These methods allow leveraging powerful pre-trained models like BERT for NLP or ResNet for image processing. Web scraping. Automated collection of data from websites using tools like Beautiful Soup or Scrapy. API integration. Accessing data through application programming interfaces provided by various services and platforms. Sensor data. Collecting real-time data from IoT devices and sensors for applications like predictive maintenance. Surveys and forms. Gathering structured data directly from users or participants for specific research purposes. Handling missing values. Decide whether to remove, impute, or flag missing data points. Outlier detection. Identify and handle anomalies that could skew analysis. Data normalization. Scale features to a common range to ensure fair comparison. Encoding categorical variables. Convert categorical data into numerical format for machine learning algorithms. Feature creation. Derive new features from existing ones to capture important relationships or domain knowledge. Dimensionality reduction. Use techniques like PCA or TSNE to reduce the number of features while preserving important information. Feature selection. Choose the most relevant features to improve model performance and interpretability. Feature scaling. Normalize or standardize features to ensure they contribute equally to the model. Missing data strategies. Complete case analysis, dropping missing values. Mean or median or mode imputation. Predictive imputation using machine learning. Multiple imputation for statistical analysis. Categorical data encoding. One-hot encoding for nominal categories. Label encoding for ordinal categories. Target encoding for high cardinality features. Embedding for deep learning models. Data augmentation is a powerful technique to increase the diversity and size of your training dataset without actually collecting new data. For image data, common techniques include rotation, flipping, scaling, and color jittering. In natural language processing, methods like synonym replacement, back translation, and text generation are used. For time series data, techniques such as time warping, magnitude warping, and jittering are effective. These methods help improve model generalization, reduce overfitting, and enhance performance on various AI tasks. Embark on a comprehensive journey through the world of artificial intelligence. This presentation covers essential AI tools, practical applications, advanced topics, and career opportunities. Whether you're a beginner or looking to advance your skills, you'll find valuable insights to navigate the exciting AI landscape. TensorFlow, Google's open-source library for machine learning and neural networks. PyTorch, Facebook's dynamic neural network library with strong community support. Keras, high-level neural network API, user-friendly for quick prototyping. Scikit-learn, versatile machine learning library for classical algorithms and data mining. Core concepts. TensorFlow operates on tensors, multidimensional arrays of data. It uses a static computational graph for efficient execution. Getting started. Install TensorFlow using pip and import it in your Python script. Begin with simple operations and gradually build complex models. Dynamic computation graphs. PyTorch allows for on-the-fly graph creation, enabling flexibility in model design. Tensor operations. Manipulate multidimensional arrays efficiently with GPU acceleration. Autograd for automatic differentiation. Simplifies backpropagation by automatically computing gradients. User-friendly interface. Intuitive API for rapid prototyping. Back-end flexibility. Works with TensorFlow, Thuano, or CNTK. Pre-trained models. Access to a wide range of models. Custom layers. Easy to create and integrate new layers. Data preprocessing. Standardize and normalize your data efficiently. Model selection. Choose from a variety of algorithms for classification, regression, and clustering. Model evaluation. Use cross-validation and metrics to assess performance. Feature selection. Identify the most important features for your model. Interactive coding. Write and execute code in cells, perfect for data exploration. Rich media output. Display charts, images, and tables in line with your code. Markdown support. Document your work with formatted text and equations. Collaborative features. Share notebooks easily with colleagues and the community. Automation of tasks. AI is widely used to automate repetitive and time-consuming tasks, improving efficiency in industries like manufacturing, customer service, and data entry. Data analysis and decision-making. AI algorithms can analyze vast amounts of data to identify patterns and trends, supporting informed decision-making in sectors like healthcare, finance, and marketing. Personalization and recommendation systems. AI powers recommendation engines in platforms like Netflix, Amazon, and Spotify, tailoring content and product suggestions based on user preferences and behavior. Image classification. Categorize images into predefined classes using convolutional neural networks. Object detection. Identify and locate multiple objects within an image. Semantic segmentation. Assign a class label to each pixel in an image. Face recognition. Detect, analyze, and identify faces in images or video streams. Tokenization. Break text into individual words or subwords. Sentiment analysis. Determine the emotional tone of text. Machine translation. Automatically translate text between languages. Text summarization. Generate concise summaries of longer documents. Audio preprocessing. Clean and normalize audio signals. Feature extraction. Convert audio into meaningful representations. Acoustic modeling. Map audio features to phonemes. Language modeling. Predict word sequences based on context. Content-based filtering. Recommends items similar to those a user has liked in the past. Uses item features to find similarities. Collaborative filtering. Suggests items based on preferences of similar users. Utilizes user-item interaction data. Hybrid approaches. Combines content-based and collaborative methods for better recommendations. Addresses limitations of individual approaches. Natural language understanding. Interpret user intent and extract key information from messages. Dialogue management. Maintain context and guide the conversation flow. Natural language generation. Produce human-like responses based on the conversation context. Integration. Connect chatbots to external systems for data retrieval and actions. Generative AI. Create new content like images, text, and music using deep learning models. Reinforcement learning. Train agents to make decisions through trial and error in dynamic environments. Ethical AI. Address bias, fairness, and transparency in AI systems. AI safety. Develop robust and reliable AI systems that align with human values. GPT architecture. Transformer-based models for natural language understanding and generation. Fine-tuning. Adapt pre-trained models to specific tasks or domains. Prompt engineering. Craft effective prompts to guide model outputs. Ethical considerations. Address biases and ensure responsible use of powerful language models. Agent. The entity that learns and makes decisions in the environment. Environment. The world in which the agent operates and receives feedback. Reward. Feedback signal that guides the agent's learning process. Policy. The strategy the agent uses to make decisions. Fairness in AI. Ensure AI systems treat all individuals and groups equitably. Implement fairness metrics and bias detection techniques. Transparency. Make AI decision-making processes interpretable and explainable. Use techniques like LIME and SHAP for model interpretability. Accountability. Establish clear responsibilities for AI system outcomes. Implement governance frameworks for ethical AI development. Robustness. Design AI systems that perform reliably under various conditions. Alignment. Ensure AI objectives are compatible with human values and intentions. Containment. Implement safeguards to prevent unintended AI system behaviors. Long-term impact assessment. Consider potential societal and ecological effects of AI deployment. Problem definition. Clearly define the problem you want to solve with machine learning. Data collection. Gather and pre-process relevant data for your model. Model selection. Choose an appropriate algorithm based on your problem and data. Training and evaluation. Train your model and assess its performance using appropriate metrics. Cloud deployment. Scalable and flexible hosting on cloud platforms. Edge deployment. Run models on local devices for low latency applications. Containerization. Package models with dependencies for consistent deployment. API integration. Expose model functionality through well-defined APIs. Model compression. Reduce model size and complexity for faster inference. Hardware acceleration. Leverage GPUs and specialized hardware for improved performance. Quantization. Use lower precision arithmetic to speed up computations. Caching. Store frequently used results to reduce redundant computations. Scope definition. Clearly define project objectives, deliverables, and constraints. Team assembly. Bring together data scientists, engineers, and domain experts. Agile methodology. Implement iterative development cycles with frequent stakeholder feedback. Monitoring and evaluation. Track project progress and assess model performance in production. Data scientist. Analyze complex data and build predictive models. Machine learning engineer. Design and implement machine learning systems at scale. AI researcher. Advance the field of AI through cutting-edge research. AI ethicist. Ensure responsible and fair AI development and deployment. Engage with online platforms offering AI courses, competitions, and forums. These resources provide valuable learning opportunities and connect you with the global AI community. Stay updated. Follow AI research papers, blogs, and conferences to keep up with rapid advancements. Practical projects. Apply your knowledge to real-world problems and build a strong portfolio. Networking. Connect with other AI professionals and participate in local meetups or online communities.